All right. So we will be discussing basically chapter 13. And chapter 13 is about acid, base. So acid-base balance. We previously talked about, and we know what is acid, what is base, what's the definition of acid, what's the definition of a base. We pretty much are familiar with, but for the sake of an argument, let's talk about what is acid, what is base. In chemistry, we're talking about, let's talk about the scale. It's a little easier for us to understand when we're bringing a scale to the conversation, to the concept. So from 0 going onward towards 7 and going to 14. This breakdown in chemistry is known for the acid-base reference. For example, if we wanted to talk about water in terms of characteristic of water, we talk about and we give some sort of a measurement. Besides the fact that we know water is H2O, 2 hydrogen and 1 oxygen, we also give some sort of a property of the water at certain degrees. So we can understand. For example, we're saying at 0 degrees Celsius equals 32 degrees of Fahrenheit. At these degrees, which are equal under both temperature reading, water freezes. That's a property of the water. And at 100 degrees of Celsius, on the other hand, it's going to be 212 Fahrenheit. Water from liquid state enters into a gaseous state. It becomes into it goes into evaporation property or characteristic. So for us, it's really good, and we can have a point of reference and understand about the characteristics. So we're going to do the same thing about the acid-base balance as well, that when we're talking about acid-base balance comes from the fact that this is how we know. They have done a very complicated calculation based on logarithmic calculation, and they came up with this, that 7 is neutral. As we go towards 14, we're talking about we're going towards base, and as we go below 7, we're going towards acid. So anything 7 up, 7.1 and up is going to be basic. So 7.1 all the way to 14 will be the base side. The farther we get from the neutral side, the greater or the intensity or the strength of the base or acid will get stronger. For example, when we are talking about, for example, 7.5 pH versus pH of a 13, 13 has more base than 7.5. That's the difference right there. That's what we're talking about. In the other opposite side, also the acid side, this is true as well, that when we leave the 7, let's say we get to 6.5, pH of a 6.5 versus pH of a 2.5. 2.5 is more acidic. The reason we do measurements and the reason we do all these calculations is because we want to give some sort of a point of reference. Based on the reference, we can do comparison. We have to have some sort of a point of reference because we can compare. 7 is less base than 13, just because we have 2 points. This is true about acid-base balance. Now, this is the understanding of, this is acid, this is base, okay, we got it, numbers are good, numbers are looking good. So what we're going to talk about is, our pH. We know. What is our pH? pH of a blood normal is 7.40. We talked about earlier about this, that 7.4 is towards base. So the structure, this is the pH of a blood, meaning that our blood by default is basic. So our blood is basic. Basic meaning is base rather than simple. I'm not talking about basic being basic, simple, rather than basic being acidity, alkalinity. So it's alkalinity, that's what we're talking about. We're talking in reference to pH. And the reason behind it is because we are constantly producing acid. What does that mean? Well, let's go with the little diagram here, because that may even clear that up for us as far as knowing what we are talking about. What we are talking is at your tissue, at our tissue level, and these are to be our cells. At our toes or fingertips, far away from our heart or lungs. We're going to talk about that. What we do produce CO2. And as you know, when we produce CO2, and we produce a lot of it, and you can think of a CO2 as trash, as a waste that we don't want to have in our body. And because we produce a lot, partial pressure of a CO2 inside the cell increases. So because it increases, everything moves by pressure gradient. So it moves out. When it moves out, now it enters into another structure, which we know as capillary. In capillary, what we have so it enters into the capillary, and inside the capillary, of course, we have plasma. And inside the plasma is the yellowish liquid that if you cut your finger, you will see it comes out. Or after, if you pick your little scab, open up, you're like, oh, something came out, plasma. So that's plasma. And that plasma has a lot of nutrients, a lot of material in it, such as albumin and other proteins and so on and so forth, sugar and stuff like that. So inside the plasma now, CO2 diffuses into, CO2 is a gas, it dissolves into plasma, just like the CO2 you have in your soda. You have CO2 in your soda. When you open the can or a bottle of Coke, you will hear this is a CO2 that is dissolved inside the soda. You opened up, you introduce a lower partial pressure for CO2. Inside the can is higher partial pressure because it's kept in a container. Once you open the container, now this gas has the ability to move out into the room air or to the atmosphere. Well, the same applies from your cell. These CO2 are traveling and going into the cell. And then once they go from the cell into the capillary, they get dissolved. So we have dissolved portion. This is about CO2, of course. So maybe I should do blue indicating for CO2. So that's our CO2 molecule, perhaps. So now CO2 is inside. Dissolved is one way of carrying the CO2. So one way is dissolved. Number two is combined by hemoglobin. And number three is in the form of a bicarbonate. So 3 ways CO2 are carried around inside the blood. Well, from this, chemists realized that, well, there has to be a way for these chemicals to be carried around. Well, the formula that came up with is CO2, which we know, plus water. That water, of course, is inside the blood. Blood is built up and made up of a lot of water. That made up carbonic acid. That carbonic acid inside the cell becomes broken down to, because this acid has a property of losing the electron from hydrogen, and then hydrogen becomes protonated, or we call it hydrogen ion, and then we have bicarb also. This is what we have inside of our body. We call this a buffer system. And when we call this a buffer system, look at what we have. We talked earlier about pH 7.4 in our blood. We said our blood is basic. The reason is basic because we are constantly introducing hydrogen ion or CO2 into the system. If the system is base, we are adding acid to it, it's not going to face so much of a disturbance. However, if the system was acidic itself already, then the situation we would have would be more acidic condition, and that's not safe. What we need a homeostasis. We need some sort of a system that can maintain life without going to a large disturbance. We have minimum disturbance. That's why our normal pH is between 7.35 to 7.45. If you look at it, it's a pretty narrow window of change that our body is able to handle and to function well. And the reason behind it, because if the body becomes too acidic or too basic, then proteins are not going to function. And our body is working, pretty much we can say the messengers in our bodies are proteins. So those proteins need to function. How are they going to function? They cannot function under such a high disturbance. The disturbance can be only a little bit. And if you look at it, is the disturbance that our body can handle is what? 0.1. 0.1, not 1, 0.1. That's a pretty narrow window that our body functions. So that's an amazing part about our body, pretty much. That's what we're saying. So then we're going back to our equation. So this whole system as we have here in the capillary, in combination of a dissolved portion, hemoglobin and bicarb, we're talking about the buffer system. Buffer system means, what does buffer system mean? What does buffer mean? The word buffer. Buffer pretty much basically means that stabilizer, neutralizer, or prevention of large disturbance. So buffer means you're going to, whatever system you have, that system allows the least possible change or control the change. It allows the system to function without going to disturbance, because a large disturbance will cause malfunction or dysfunction. So we need a buffer system. Now, we have the CO2 came out of the cells with water, became carbonic acid. And then on the other hand, we have hydrogen ion and we have bicarb. This system, as you see, arrows shows both ways. It goes back and forth. This is true because at the cell, we do produce a lot of CO2. So this equation or this formula goes towards right. It's shifting towards right. It goes towards right. And then this happens, and it's keep going up and up and up. And we're not done with this, because this is keep going up and up and up and up. And we have another way of looking at this. Now, this will go the other way around as we had it. It becomes carbonic acid all over again. And of course, we have our friend CO2 and water. Now, this is the moment that we're going to talk about where are we? This is at AC membrane, exactly. This is at AC membrane, excellent. So we're talking about AC membrane, of course, and if we want to be precise, we're talking about alveoli per se. But of course, alveoli by themselves are not going to do anything. It has to be, and I will put it in red to indicate that we are still at the capillary. So even though we're going reverse, doesn't mean that we are away. We are still at the capillary side. So this is at the capillary. So we're going to look at this and see what changes are taking place. So at this point, the CO2 will start going out. Will start like going out. Some of the water also goes out as well. So we want to know this is at the cells and tissue, and this is at the alveoli, and we are talking about lungs. So our buffer system takes a lot of shock, just like a shock absorber. That's the buffer system of our body does. Shock absorber does this. It receives a lot of hit, a lot of pressure, a lot of force in the car. And then it takes that pressure and it releases the pressure, the least minimum, to the passenger, to the seat, to those people who are riding in the car. So as a result, when you're sitting in the car, you're not really feeling every hit on the road, but rather a little disturbance, a little movement. The same applies to our buffer system in our body. So again, to recap, our cells produce a lot of CO2. How much CO2 are we producing every minute? 200, thank you, 200 milliliter per minute. That's how much CO2 we are producing. This CO2 will dissolve into our capillary. And what we have is we have higher concentration, of course, from cells, goes into, so as a result, what do we do now? Combined with O2, carbonic acid, hydrogen ion, and bicarb. Now we are traveling and going near lungs. We're talking about going back into the right side of the heart, and we're getting close to the alveoli. That's where we are. Have to put the chargers so we can record for those who are not here, so they're not missing a lot of stuff. Okay, so this is what we have done. And we're not done. This is just the beginning of what chapter 13 is going to talk about. So we're going to do this little base, and then we're going to talk about the rest of it, because the rest will be easier as we get to this part and we understand that. So CO2 you're going to send that out. Through the lungs, you're going to exhale it out. Beautiful, perfect, everything is good now. Water also goes out of your lungs. You call that water vapor? Correct. But what kind of a loss it is? What kind of a loss you have? This is water loss. When you're urinating, that's a sensible loss of water because you can sense it, you can measure it, you can see it. But you have something else, you call it insensible water loss, which is through our skin and through our respiratory system. So you have some water loss also. CO2 is controlled, and we are talking about during exhalation, of course. So this takes place during exhalation. We need to understand that part. And this is as far as how. And when we are looking at this buffer system, you're going to know that this buffer system is referred to as open system. Because it is open to outside. Because it is open to the outside world by exhalation, you're removing a CO2, you're not having it anywhere else. So we have another buffer system which is closed, which is not open to outside world. Well, it keeps the component inside the body and it's not releasing it out. So we want to look at and see what's going on with the hydrogen ion. As we discussed previously, hydrogen ion has an important role. And the role of a hydrogen ion is that hydrogen ion does a lot of things for us. Hydrogen ion, for example, it does activate some part of the body for us that it does affect the breathing, and that is central chemoreceptor. Central chemoreceptor becomes activated by hydrogen ion, and it travels, and what it does to central chemoreceptor, it activates the central chemoreceptor in such a way that central chemoreceptor starts firing up even more, and as it fires more and more, our ventilation is going to increase. So this is what we want to know, that hydrogen ion will activate central chemoreceptor. Central chemoreceptor starts increasing the firing, meaning that sends signal through a nerve that is originated from C3, 4, and 5. And that is the nerve we call phrenic nerve. And that phrenic nerve responds by activating a muscle, which is extremely important for our breathing, and we are referring to diaphragm in that case. Diaphragm does 75% of the work of breathing. This is extremely important for us to understand because hydrogen ion has a lot to do. Meaning, for example, that if our CO2 production goes up, normally is at rest is 200 milliliters per minute. If our CO2 production goes up and it gets doubled by, for example, if it gets, let's say, 400, which is double of that, then meaning hydrogen ion level went up and stimulated the central chemoreceptor at the greater level. I'm going to put 2 arrows. As a result, diaphragm is going to work double, so the work of breathing will be double, meaning that your minute ventilation will increase. Just because you produce too much CO2, your body's response is going to be helping the body to get rid of extra CO2. So our breathing is controlled. The mechanism of our breathing is controlled, and it is based on removal of CO2. If we have built up CO2, body becomes acidic, This is something that we're trying to prevent. We just don't want that. When we're talking about when we are going over chapter 13, materials that we see in chapter 13. So we're going to start from the beginning, and it says, for example, volatile acid. Well, volatile acid, we are talking about the reference to volatile acid is carbonic acid. Because carbonic acid is going to be exhaled in the shape of a CO2 out of the lungs. And volatile means evaporation or evaporating, easily became into a gaseous state. From liquid becomes into a gaseous state. It says a volatile acid is one that it is in equilibrium with a dissolved gas, meaning that whatever amount of a CO2 I have at this point, I will have that amount of a carbonic acid on this side. If my CO2 goes up, carbonic acid will go up. And then if my CO2 go down, so as the carbonic acid will go down. That's what it means. So volatile acid is in equilibrium with the dissolved gas. And the gas we're talking is CO2 at this point. Then we have other acids that are not volatile, non-volatile or fixed acid. Non-volatile, here's an example. Volatile acid, will lose it all the time in the form of a CO2. Non-volatile acid, we don't lose them because they are part of a closed buffer system and they remain in the system. So we don't lose them. They're getting recycled and recycled in the body. That's the difference between the two. So, having said that, now we're going to talk about some. Let's go to page 293 in your book. And we have the same diagram. When we are talking about increased minute ventilation, I want you to know that we are basically or mainly referring to increased alveolar minute ventilation. Because minute ventilation has two components. It has dead space minute ventilation and alveolar minute ventilation. But our concern is increased alveolar ventilation. Because if you increase the dead space ventilation, what is that going to do for us? Pretty much nothing. You're just moving the air in and out, and you're not having any gas exchange done. Not necessarily that is something that we're looking forward. What we're looking forward is alveolar ventilation. So what you want to know, what you want to highlight and you want to know is that page 294, buffer solution characteristics, on the left column, the heading says buffer solution characteristic. You want to highlight the first sentence and second sentence, where it finishes with mixtures of acids and bases. That's what you want to know. And then lower on the same column, bicarbonate and non-bicarbonate buffer system, you want to highlight 4.5 lines. It ends including hemoglobin. So you want to highlight those lines. And then going to the next column, starting the paragraph, this is the bicarbonate system. You want to highlight to the end of the sentence, which is by ventilation. And another paragraph which is below the formula, the chemical formula, and non-bicarbonate, you want to highlight to the end of the sentence. That sentence is actually like 2.5 lines. Box 11-1 is a very good, is a really a good 13-1, I'm sorry. Did I say something else?
Just 11.
11, oh yeah, I'm sorry. Yeah, I saw 1 in there, I thought it was 11, but it's not. I got my math wrong. So 13-1, box 13-1 in page 294, that's a really good summary of what we're talking about. Open system has bicarbonate, we talked about, that's the main one, and plasma and erythrocyte, which is red blood cell. And then we have closed system, which is non-bicarbonate, which means it does not have carbonic acid in it. Hemoglobin is one of them. Of course, there is no carbonic acid in hemoglobin. Organic phosphates, inorganic phosphates, and plasma proteins. So it's something good for us to know. Then we can go to page 295, and on the left column, and you want to count down 2, 4, 6, 7 line, and towards the end of the 7th line, where you're going to start highlighting, it starts with bicarbonate buffers have the greatest buffering capacity because they function in an open system. We talked about it earlier. Because it is open, it can do a lot of, it can remove a lot of CO2. That's what they're referring to. And if you want to look at the numbers, table 13-1 on page 294, it allows you to understand and get what we're talking about. Bicarbonate system, 53%, non-bicarbonate system, 47%. So each of them have their own designated percentage of how much they remove and what they do. Another equation which is used a lot is Henderson-Hasselbalch equation. You do not need to do the log of anything during board exam. But this equation is good for you to understand, to analyze, to realize what is going on. And the one that I'm referring to is the very first one on top, Ka. Ka, we're talking about equilibrium constant, equals hydrogen ion concentration times bicarb concentration divided by carbonic acid. This means if we have a lot of hydrogen ion, then we should have a lot of carbonic acid, so as bicarb. We'll get to that part, and we're going to look at it also in a little bit. Page 296, right below the equation that they have done an example. In italic, you want to highlight this that says blood gas analyzers. We're talking about ABG machines. Measure pH. The first formula. So you want to look at the first formula. Yeah. Yes. Blood gas analyzer measure pH and PCO2, but compute bicarb. But this is something interesting, is good for us to know. So they measure the pH and PCO2 just like you're measuring with the scale. And then computes. Out of finding those two, it does the computer does the work. And what does it do? Calculates, get the log of a Henderson-Hasselbalch equation, and then find out what's going on and how much we have bicarb in the blood. Under the heading, lower down the column, under the heading bicarbonate buffer system, you want to highlight the first sentence, which is 3.5 lines. The bicarbonate buffer system is particularly effective in the body because it is an open system. That is, one of its components, CO2, is continually removed through ventilation. So far, whatever we talked about, we'll keep talking about the same thing over and over and over. But the only difference is we are looking at it with a different perspective. One perspective is how this gas is dissolved, then how this gas is combined with hemoglobin, then how this gas is transported in the shape of a bicarb. That's what we're saying. So we have a same story, we have a same incident, but we're having 3 different people are saying the stories to us from their point of view, from their wording, with their wording, from the equipment they had. It's like you gave them 3 cameras and they went to this event and they recorded some video for us. Every single one of them are exciting just because from they had a different angle and they gave us a different angle on the same event. Table on the right column, page 296, table 13-2 is a good summary that you want to become familiar with, that bicarbonate is open, non-bicarbonate is closed. Page 297, you want to highlight the first sentence on the left column. The bicarbonate buffer system can buffer only fixed acid. And then the next line, the bicarbonate buffer system cannot buffer carbonic or volatile acid. You want to highlight that. Under the formula CO2 plus water, under that formula, that paragraph, the last sentence of that paragraph says the closed non-bicarbonate buffer systems are the only buffers that can buffer carbonic acid. You want to highlight that. Non-bicarbonate buffer system, under that heading, second line, hemoglobin is in italic, it starts, and you can highlight that. Hemoglobin is the most important because it is the most abundant. This is under non-bicarbonate system. 2 lines down, towards the end, it says, however, we're talking about hemoglobin, they can buffer hydrogen ion produced by any acid, fixed or volatile. So their capacity is extremely high because, first of all, hemoglobin is found all over the body. As a result, they have a higher capacity to handle, to digest, to do whatever it needs to be done, fixed or non-fixed. They can get rid of it. They can clean up. That's the beauty about hemoglobin. So again, once again, we realize and we understand that hemoglobin has such a great impact and function in our body. And you want to go down in the same column towards the end. Towards the end where you have the formula and all that at the bottom, right above it, like 3 lines up, it says both open and closed system. So you want to go down? Yeah. Sylvia, you got it. Yeah, you're right. You're right. Both open and closed system function in a common fluid compartments, which is blood plasma. Both open and closed system function in a common fluid compartment, blood plasma. So in blood plasma, here in blood plasma, we have open system and we have closed system. Open system, we know what it does. It is open. by the means of a CO2 and it goes out. It's a volatile acid. Closed system, you don't exhale this one out. It remains in the body. It remains in the system. That's your, and hemoglobin also. This hemoglobin right here, another one. This hemoglobin remains in your system. It's a buffer system. It's a part of a closed buffer system. It's not going anywhere. It will stay with you. 297 under the heading says acid excretion. You want to highlight the first sentence, which is the first two lines. Bicarbonate and non-bicarbonate buffer systems are immediate defense against the accumulation of hydrogen ion. And then again, if you look at it, how many buffer systems? Two. One helps the other, second helps the first, first helps the second. It comes at least two just because they help one another. Next paragraph. The lungs and the kidneys are the primary acid excreting organs. We already know that because we already studied ABG. We are familiar with that. Correct. You want to highlight this one. The lungs can excrete only volatile acid. An example of a volatile acid is the CO2 from dissociation of carbonic acid. Pretty easy, pretty straightforward, you know it. But we're going to touch base on the basics also as we go along. Under lungs, the heading lungs, you want to go 2, 4, 6, 7, 8, 8 lines, and it starts with carbonic acid. You're going to see H2CO3. You want to highlight that. It says generated by both pathway is eliminated as CO2 through the lungs. That's the beauty of the lung. Doesn't matter. It does the job. It works that way. It cleans up regardless. And then you see kidneys heading. You want to know the first sentence. Kidneys physically remove hydrogen ion from the body. And then 3 things you need to know about kidneys as far as terminology to understand is the following: excretion, secretion, and reabsorption. So be sure to know those 3 words and be familiar with that. 298, third line towards the end, the starts. In addition to excretion of a bicarb, the kidneys influence blood pH by retaining or excreting bicarb. You already knew it. This is not something new to you. Third line towards the end. And the last sentence of this left column, third line towards the end. Towards the end, go, there you go. Yes. That's okay. And the last sentence of this paragraph, if you go down, the only thing I want you to highlight, because you already know it, of course, right in the middle, it says the renal process is a slow. Same paragraph, right above the basic kidney function. Basic kidney function heading, third line towards the end in italic. The glomerulus is the component of the renal nephron responsible for filtering the blood. And the one that you want to be easy and slowly studying and learning it, and also what you want to do is you want to get comfortable with is figure 13-2. Renal response to respiratory acidosis. This figure tells us how body, kidney, responds to respiratory acidosis. So you want to do is respiratory acidosis means CO2 went up. which means you had hypoventilation. Now, what does kidney do? So, kidney needs to go the other way around. So, reabsorption of bicarb, you meant.
Yeah.
So, if we have a lot of CO2 in our body, our kidney has a tendency to reabsorb bicarb, elevate. We are acid. We want to elevate the base part. Because if you look at it, let me explain one thing to you, which is really easy for us to understand, if we can understand this part. And this is this. This is the part I want you to understand that. When we are talking about acid, let's say about carbonic acid, because this is the one we are dealing with a lot. Carbonic acid has two components, hydrogen ion and bicarb. This is the acid. We know that. Hydrogen ion is the one that promotes acidity. Bicarb is a conjugate base. What is conjugate? So you want to look up what is conjugate. Exactly. Conjugate base is this. These two are together making up this. So if I break this down, I have hydrogen ion, and what is left is a conjugate base of this acid. It's a component of this acid, which is a conjugate, we call it conjugate base of this acid is bicarb. So bicarb is the conjugate base of carbonic acid. So when we are saying that, meaning that if in order for the body to function, when hydrogen ion went up, CO2 went up. Hydrogen ion will go up. It went up. Your body said, because hydrogen ion goes up, meaning that we have acidity condition going on. In order for the body to compensate, to become neutralized, to get to a normal level, what do you need to do with your conjugate base? You need to go up on the conjugate base also to keep it in check. That's what they're saying. That's what they're explaining. And it's pretty easy and straightforward when we're looking at it this way, that, for example, you went to store and you paid for 2 pounds of meat. In one hand, you give money to the cashier for $10, 2 pounds of the meat. In another hand, you should receive 2 pounds of the meat. Same thing. If you have too much of an acid, you need to have in return too much of a base also in order to keep it in balance. It goes to our buffer system. You do not want to have too much of a one thing. You want to have too much of a two things at the same time, so you are not introducing a large or great disturbance. It all goes back to physiologic factor of the body. Too much disturbance is going to kill us. As a result, we need to have mechanisms. These are all the mechanisms that help us maintain and handle such a large disturbance or such a heavy disturbance. Control it to become minimum and minimum, just like a shock absorber. That's what it does. So that picture explains it pretty well. So in order for you to understand this picture, you just need to slowly read and take your time and become comfortable with that. Because this is understanding, this is concept. This is concept, and you just want to, and when you highlight, the area that I tell you to highlight are the area that are essence of what I'm asking you to highlight. You don't want to highlight your entire book. There is a reason behind that. Because what it does to you, now you don't know what to focus on. So whether you want to do underline with blue pen or red pen or pencil, whatever you want, or you want to highlight, this is, your goal should be this. to read one paragraph, and you should be able to highlight 1 to 2 sentences of each paragraph maximum. Because the essence, the soul of that paragraph resides in 1 or 2 sentences. The rest are supporting. Thank you. Topic sentence. Good. Very good. 298, right column. 4th line towards the end. The sentence starts with this, but you want to highlight the rate of hydrogen ion secretion is almost the same as the rate of a bicarb filtration. So 298, right column, 4th line, towards the end of that line, the rate of a hydrogen ion secretion. And then you want to go down in that column all the way down. You want to highlight the last sentence. Any factor that increases PaCO2. You want to highlight that. These figures are really helpful visualizing and understanding, putting it into perspective one to another. 299, figure 13-3, renal response to respiratory alkalosis. Because we know our body responds. Renal system responds to respiratory, respiratory responds to renal. So that's another one that you want to highlight. Page 300. Left column, all the way down when you see italic word, you want to go ahead and highlight that sentence. People with chronically high blood PCO2 tend to have low blood chloride or hypochloremia. That's something you want to keep that in mind. There is a reason. So the reasoning behind it, it can be found in the area that we talked earlier, or chapter 11. You lose chloride ion, hamburger shift. You want to know that one. Correct. Yes. Page 300, right column. Under acid-base disturbances, heading towards the end, about 3 lines before ending that column, it says, or right below the formula, you will see it says, as long as the ratio of bicarb buffer to dissolved CO2 is 20 to 1, the pH is normal or 7.40. So what it says, the ratio of a bicarb to CO2, the ratio there is a ratio in between. And the reason we put it in a bracket, we're talking about concentration. This ratio, according to our book, says is 20 to 1. As long as we have 20 bicarb to 1 CO2, then pH is 7.40. If this changes, then we have disturbance. If it remains differently, for example, let me see if it gives us any example or anything like that. Okay, so it does give us an example. If for any reason we have 25 to 1 or 15 to 1, then we have some sort of an issue. We have some sort of a problem there. If it is 25 to 1, look at what is happening. We have extra bicarb. What do we call that? right? And what about if we have lesser bicarb? That's it.
We know that too.
Of course. But again, we're looking at the same topic with a different lens and camera, with the different people are telling us the story. So you highlighted that, that's good. Page 301, you want to look at page 301, left column, right above the heading, primary respiratory disturbance. You want to know pH is normal 7.35 to 7.45, PaCO2, bicarb, and then you want to highlight the rest, which is italic, alkalemia, acidemia, hyperventilation, and hypoventilation. What you want to do is you want to study these and you want to come back to it and test yourself. You understand when you're writing down normal value is 7.35, 7.45, and now all of a sudden pH is 7.20. Okay, what does that mean anyway? In terms of ventilation, in terms of removal of the CO2, what does that mean to you? You want to make sure that you understand that part, because you understand the numbers, you can read the numbers, those are easy. But we just need to understand other parts that comes with. Page 302. You can test yourself and you can check whether you're able to write certain ABGs or not. And the best summary you can have is table 13-3. It talks about primary effect of a respiratory acidosis. And then it talks about compensatory response. That's something we're talking about concept understanding. Because acute is something that all of you guys understand pretty well. It's easy, everyone understands. Compensation comes with concept and understanding and applying the knowledge you have into a given situation. So that takes a little time for sinking in and owning it and knowing. Page 302, left column, as you go down, you will see that it says, where you would see right above compensation, restoring pH to normal. Right above that, there's a paragraph. And right above that paragraph, second line, it says, an individual may lose HCl, chloride, acid, HCl is chloric acid, from the body by vomiting. That's something we want to keep that in mind, because chloric acid is part of a non-volatile. You don't exhale it out. If you lose it, then your body will be deficient of that. Vomiting large amounts of a gastric juice. If that happens, then your body turns into a different situation as far as being, if you lose a lot of acid, then you're going to have less of the acid. You're going to turn into metabolic alkalosis. Compensation. So under compensation, restoring pH to normal, second line, you want to start highlighting in hypoventilation till end of the paragraph. Page 303, rule of thumb is something that National Board like to test and ask questions. These are pretty common questions that show up. For an acute increase in PCO2, the plasma concentration of a bicarb increases by 1 milliequivalent per liter for every 10 millimeters of mercury. So for every 10 millimeters of a mercury increment of a PCO2 greater than 40 millimeters of a mercury, that's a lot. So we just want to keep that in mind. And if you look at it, it goes up 1, and it affects the PCO2, 10 millimeters of mercury. Be sure to study mini-clini. All the mini-clini that you see are extremely important and vital for you to study and know it, because it helps. It helps greatly to tackle these questions and understanding what's going on, where everything are going. Page 304 teaches us how to study and read ABG. For example, it says first, categorize the pH. Like try to find out try to find out what's going on with the pH. Is that acid, is that base, is that normal, or what is it? And then talk about PCO2. Is that normal or is not? Because every time when you're looking at the pH or you're looking at the ABG, you want to find out about pH first and foremost, because pH tells us about homeostasis, and that's important. Once we know homeostasis is not in danger zone, then we're going to look at PCO2, whether it is or is not. First, we're going to look at the pH. Then we're going to go to the second step, which is PCO2. We're going to look at the PCO2, and we're going to find out if we had any disturbance of a pH. Was it involved? Was it indicated because of a PCO2? Or it was influenced by bicarb? Like, your question is always going to be in this regard, that who contributed to the disturbance? If you have any disturbance. If your pH is normal, then you don't have any disturbance. But it's still, you're going to look at PCO2 and bicarb, because you're going to look at their level. Are their level normal, or is just like you have a chronic individual? We have a chronic patient which their measurement will be elevated or decreased, but the pH is normal. But overall, we just want to look at the pH to find out if we have a normal pH, homeostasis is in danger, or homeostasis is in normal shape. So we want to look at that. We just don't want to forget about that part. So that is about reading, which you guys are familiar with. You guys are pretty good as far as the reading goes. You can read anything. And the summary of what we just said about the increase and decrease of a bicarb influence the pH and PaCO2 are found in page 306 and table 13-6. The really good thing about this chapter is they put a lot of mini-clini, which are applications of whatever we study. So mini-clini you want to study, and you want to read it, and you want to understand it. And these are pretty good questions that you might end up having and using. So just take a look at it, make sure you know it. Page 306, under that mini-clini right column, we have something that says causes of respiratory alkalosis. So last sentence, right column, says the most common cause of hyperventilation in patients with pulmonary disease is decreased PaO2, which we know as hypoxemia. This is something you want to, so remember from this point on, when you study, when you read any part of the chapter and you do hear the most, the least, you want to highlight and you want to know it. You want to put it on a flashcard. It says this is a landmark for this or that. You want to put on a flashcard, you want to memorize it, and you want to own it forever. And it says, is marked something. Anything when it says marked You want to memorize it and you want to know it because it will show up. And you're responsible to know it because they are talking about emergency. And during emergency, no one handles the situation in allied healthcare, in hospital such a setting. No one, sometimes not even physicians or any other healthcare providers. The most calm and collected and well-rounded are RTs because we show up to crisis all the time. We get good at it. We're really good at it. And our training, of course, it puts us there. So we want to know that. Okay, so page 308, you want to go to page 308, left column, first paragraph, second sentence. It starts with this. This example show that blood gas data alone are insufficient for rational acid-base assessment. So we're not going to just look at the data in front of us. We're going to look at a couple of other components also. Is my patient on O2? Is my patient being on a mechanical ventilator or not? Is my patient has a history of so and so or not? We're going to look at that as well. And then under metabolic non-respiratory acidosis, the causes, number one, number two, you want to highlight. First, second, and third line. And right column under anion gap, where it says anion gap equal the formula, equal to sodium concentration, that formula. The paragraph that follows, the last sentence you want to highlight where it says the normal anion gap range is 9 to 14 milli equivalent per liter. Are we good? Okay. Oh, okay, good. Very good. Page 309. Page 309. That paragraph on the left column, you want to highlight the last sentence of the top paragraph. A high anion gap indicates that fixed acid concentration in body has increased. That's what anion gap says. So anion gap, a high anion gap concentration says fixed acid concentration in the body has increased. 309, right column, under symptoms, bottom. Fifth line towards the end, you want to highlight that. And you want to know this forever and ever and ever. It's MBRC's favorite. And it will show up. And a lot of people will ask you because we'll have a lot of patients who are having diabetic situations. So we deal with it a lot. Patient with the Kussmaul respiration, yes. Page 310, left column, last heading, causes under metabolic alkalosis. You want to start highlighting the first sentence, which goes to 1 or 2 towards the end of the sentence. So pretty much highlight the first two sentences, the first two lines, not two sentences, the first two lines. Metabolic acidosis can occur in one of the following two ways. 1, loss of fixed acid, or 2, gain of blood buffer base. That's the one you want to highlight. Page 311. Page 311. You see where it says italic, third paragraph, right column, 311, italic. Normally, sodium is reabsorbed through primary active transport. Page 312. Page 312. Left column under compensation, you want to highlight the first sentence. And you want to go to the next column and highlight the last sentence also there. Or last line, perhaps, where it says, cause hyperventilation, such as anxiety, pain, infection, fever, or pulmonary edema. These are all contributing. Under this, the last sentence on the right column is standard bicarbonate. What you want to highlight is the standard bicarbonate is the plasma concentration of bicarb obtained from a blood sample that has been equilibrated with PCO2 of 40 millimeters of mercury. And 313, right column, base excess, fourth line, mid-sentence or mid-line that starts with this you want to highlight. And normal BE or base excess is plus minus 2 milli equivalent per liters. A positive indicates a gain of base or loss of acid from non-respiratory organs. You want to keep highlighting it. Negative base excess indicates a loss of a base or a gain of an acid from non-respiratory causes. So that's something we want to know, because when we're looking at the base excess, if it's up, this is positive or negative, automatically we know what's going on. Because it says, if it is greater than 2 or is plus, indicates a gain of base excess. It means you have extra base in there. That's what it means. Gain of base or loss of acid. So whatever has happened, it made it to be base, whether we have extra base or we have less acid, which means the same pretty much. Correct. Yes. So we are at the end of chapter 13 at this point. So this is chapter 13 that talks about the reasoning. Besides the fact it teaches you how to read, it talks about what is this, what is that, what is this, what is that, so on and so forth. So pretty much we're done with this chapter, but then now we have the question section. What is your question? Do you have any question? Or you need to take a little break? Yes? Okay. So let's take a break, because this way